I want to let speak for a few moments here. This is Kylie, who's one of our coordinators of our section leading program, and she's going to tell you about how to apply to be a section leader, if that might interest you. So here, take it away, Kylie.
All right, thanks so much, Marty. So as Marty mentioned, my name is Kylie, and I'm one of the coordinators for the CS 198 section leading program. So what is CS 198? CS 198 is the program that sets up all of the section leaders that each of you has, as well as for 106A, 106X, and 106AP and AJ when those are offered. So who should section lead? For this round of applications in particular, we're looking for current 106B and 106X students, and that is you guys. So we're looking for section leaders from all backgrounds, regardless of your major, regardless of what year you are. And it's just students who are interested in helping others explain concepts, as well as working with people in the 106 classes. So what do section leaders do? I'm not going to take a huge amount of time on this slide since all of you have section leaders and have interacted with your section leaders. But the main points to remember here is it is a paid job on campus. It's $17 per hour for the first quarter, and that goes up with seniority. And it's also just an amazingly fun job where you get to interact with students on a regular basis. So in terms of time and requirements, the section leading requirements are that you have to section lead for at least 2 quarters, and you will take CS 198 your first quarter for 3 to 4 units. You will attend staff meetings, which happen on Mondays from 4:30 to 6 p.m., and you will attend workshops on Monday, Wednesday evenings for the first 4 weeks of your first quarter. You'll fulfill all teaching, layer, and grading responsibilities, and it's about, we say, like 15 hours per week for the first quarter once you're starting out. So why should you section lead? We like to say learn to teach, teach to learn. Teaching is a great way to get more familiar with the concepts in addition to working directly with students. You get to participate in our staff events and join an amazing group of people while leaving your mark on campus. So events, that picture for some reason is not showing up, but we have Lair Formal at the end of every quarter. We have a new breakfast, a welcome breakfast for new section leaders. And we also have a lot of events with our sponsors and corporate partners. So we've had an Iron Chef event at Google and a cruise with Microsoft. And you'll also just get to join an amazing group of people, a fantastic alumni network, which includes Maran himself. So applications are open now. For 106B and X students, they are due next Friday, February 16th. The application can be found at that URL, and if you have any questions, you should feel free to contact me and the other CS 198 coordinators at that email address. And I can take a quick round of questions if anyone has any right now. Any questions? So, yeah, the question was if you applied, do you start in the spring? Yes, you start spring quarter and then also do fall quarter. Anything else? Great. Thank you, guys.
Thanks, Kylie. You know, Kylie neglected to mention another person who's been a section leader in his life, and that's yours truly. I was not a section leader here because I didn't go to school here, but I was a section leader somewhere else, and they had the same kind of program. I thought it was lots of fun. And it really made me feel good to help students, and it's probably why I'm here, standing here today. Got me excited about teaching, and it was a wonderful experience for me. So I think if some of you guys are getting a lot of enjoyment out of coding and out of 106B, it's something you might want to consider. We'd love to have you join our team. So thanks for that, Kylie. Please email them if you have any questions. You're also free to ask me if you have questions about section leading as well. Happy to talk to you about it. Okay, so let's do some C++, right? We've been talking about linked lists and pointers, and this is a tricky concept, so I'm sure that it still seems difficult and hard to understand, and I bet section was kind of tricky this week and all that, and that's okay, that's totally normal. We're going to keep working on it today and get more practice with it. Most Fridays we give you a new homework assignment, but the good news is we don't have a new homework assignment going out today because you get until Monday to work on homework 4, and the next assignment goes out next week, so you don't have to worry about that. Yay. Thank goodness for small mercies, right? That's about as nice as I'll ever get to you guys. So, okay, quick recap. We wrote these nodes that had pointers that pointed to each other. We chained them together to make a linked list. We wrote code that could walk across a linked list, that could traverse a list to examine all the elements or print the elements or something like that. And the key concept I showed you last time was that you often need to make this like temporary variable. I often will call it current or temp or something like that. I call it current because it's like the current node that I'm looking at right now. You use this variable to walk across the list to look at elements, and the reason that you use that instead of the existing list front pointer or whatever is because if you move the front pointer, you lose your pointer to the front of the list. You're not able to look at the list elements anymore. Okay? So that's something important that we saw last time. And so we were kind of working on this file where we were able to make a list with elements of data, and then we could make a method like print, and then the print method would take a parameter of the front of the list, and then it would, bless you, it would print out the content, something like that. Start at the front and loop until I reach null. Remember how the end of the list stores null, and print the data of the current node and then move to the next. Current equals current next. Move it to the next one, right? And so I draw these pictures of pointers, and I think it's important to understand what a line of code like this does. When you say current equals current next, you're saying I want the current pointer to point where the current next pointer points. So make this arrow point to where that one does. And so it moves it to the next one forward. You know, we have to be able to reassign pointers to manipulate a linked list. Kind of tricky at first. Okay, so what I want to talk about next here is what if we want to add an element to the front of a list? We were kind of doing that at the end of Wednesday. Insert a new node at the front. And so before the call, it stores, I don't know, 20 and 30. After the call, it says 10, 20, 30. And, you know, I don't want to loop across all the nodes and change the data. Like, I could loop across the 20 and the 30 and set that to be a 10 and that to be a 20 and then insert a new node with a 30 at the end or something. That's not what I want to do. That takes too long. Instead, I just want to make a new node and have the front be the new node and have the new node point to the rest of the nodes, and it'll be faster. It'll be a constant amount of time, big O of 1, as opposed to looping over all the nodes, big O of n. Okay? So this is a general thing that I want to do. Now, we wrote code to do this last time in the main function. Here's what we did. We had a thing that says make a new node, set the data to whatever the new value is, set the next of it to be front, and then make the front be the new node. Now, again, I think it's important to be able to look at existing code and understand what it does. So if I go back to the slide, I can draw you the output of these lines here. Let's go back and you know, I normally don't look at my phone during my own lectures, but I have to because like any day now I'm going to have a baby. So like every time my phone buzzes during class, I have to look at it because my wife's like, you better answer if I call. I don't care if it's during class, so we might get that all captured on video. We'll see. I was like, but honey, what if I'm in the middle of a really cool linked list demo? She's like, you answer. Yeah, so there's that. Yeah, where was I? Oh, so imagine that you're adding something to the front of a linked list. Okay? So let's trace what these lines of code do. New node equals a new list node. Okay, so what that does is I say new node. I make a new list node. New. I'll just call it new because I can't write very cleanly here. So new is a pointer that points to this. And then I say new node data equals 777, so I put the value into the node, right? The thing has two little boxes. Then I say new node next equals front. That means make this pointer that my cursor is wiggling on, that's the new node next pointer. Make it point to the same place that front points. So that means make this point to there, right? Make it point at that node. And I said this to you Wednesday, I'll say it again. It's not correct to say that it goes like that or something. It doesn't point at a pointer. It points at the thing that that other pointer points at. It means make this point to the same thing as this. That's what that line of code means, okay? So it means make the new node next point to here, okay? Now, I've just finished executing line 43, and I want you to understand that I'm not finished yet, that if I just stopped after line 43, I wouldn't have succeeded in adding anything to the linked list. And the reason that that's the case is because the person who's holding onto this linked list, the way that they access all of its elements is by starting at front, and then they go next, 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 right? And so even though I have added a new node, and it is sort of before the front, if the person who's holding onto this list starts at front, they're still going to start at 20. They're not going to see my new node. You understand that? Like, I don't know what the analogy is here, but like, I need to make it so that if they say front, they'll see my node, and they won't see the 20. And so that's why line 44 of this code is very important. When I say front equals new node, that means make front point where new node points. So that means don't point to the 20, point to here. So now the list, for all intents and purposes, contains 777 followed by 20 followed by 30 or whatever, right? So that's what that code does, inserts at the front of the list. All of those lines are needed for that reason, right? Okay. Do you guys understand this code? Do you have a question about the code up there and the picture there and how those two match with each other? Yeah? Oh, passing a node by reference. I'll talk about that in a second. Yeah, I haven't got there yet. Basically, I will do that. Yeah. Okay. Well, fine. So that's the code to add something to the front of a list. That seems like a useful method to have. So why don't we make it into a method? So you could imagine that we would write a method called addFront. And so where's addFront? Do we have addFront? So here's addFront, okay? So what if I just took this code and I just pasted this in here? It's the same code, right? You tell me what the front is, you tell me the value that you want to add, and I'll do all of these things. Seems like a reasonable thing to do, just like we did that with printing a list. We originally wrote it in main, and then we pulled it out into a function. Cool. Okay, the problem is that this won't work. The reason why it doesn't work is subtle. I'll prove to you that it doesn't work first, and then I'll talk about what to do to fix it. Maybe you already know what to do to fix it, but I'll show you first. So let's go to main. So instead of having this list with 42 and whatever, I think what I could do here is I could say list node front equals null pointer. Just, I don't have any data yet, but I could say add front, comma, what are the values here, 42. You know, I should be able to build a list by calling this method now. 42, or I guess it's inverse order, so it should really be 9, and then 17, and then -3, and then 40. I think if I add those in that order to the front, then at the end of all that, I'll have that list I want, 42, negative, you know what I mean, right? So, okay, my list is, so let's see what it does. My list is, here's the list again, it's nothing, it's empty, it's null, it didn't do anything. I just tested this code and it worked, but I moved it into a method and now it doesn't work. What's going on? So I want to try to explain, I mean, this is related to, you had a question, you said something about passing a pointer as a reference, and that's related to this. So I want to explain this here. So why doesn't this work? Well, here's what our code is basically doing. I'm trying to insert the front, the 10, right? And so this isn't exactly the code we typed, but it's close enough. Like make a new node, put it to the next, and then put the front equal to that node. So let me describe what happens here when this code runs. Main builds this linked list, and main says add to the front of it. When I pass the list pointer as a parameter, it passes that parameter up and calls it front inside of the function, right? But what that really means is make the front parameter point to the same place that this list variable points here. So I have two pointers. One's called list in the main function. One's called front in the add function. They both are storing the same address in them. They're both pointing to the same place. And that place is this first node. Okay? This is the state of things as add front is about to run. So what do? I say list node temp equals a new node that stores this value. So okay, make a new node, store the value of 10 in it, and have this variable temp that points to it, right? That's what this first thing does. Now I say temp next equals front. So this next should point to where front points, which is over here, right? This all looks pretty good, right? So now I say front equals temp. So that means make this guy point where that guy points. So do that, right? This is all really good stuff, except this list front pointer here didn't get updated. This parameter front got updated, but they are separate. They are two pointers that point to the same place. If I change one of them to point some other place, it doesn't affect where the other one points to. So again, if I say front equals temp, it does that. But it doesn't change the variable from main. So anyway, that's what's wrong. That's why it doesn't work. But it turns out that we've actually solved this problem a long time ago in terms of like, I have a value in main, I want the function to be able to directly change it. The way we do that is either by returning the value or by passing the thing by reference, right? And so it's a little weird to do so, but you can pass a pointer by reference. If you pass a pointer by reference, what it means is simply just that you're sharing the pointer from main to the other function, and if the function modifies the pointer, the change will be seen in main as well. That's all. That's what reference parameters are. You already know that. It's a little weird to do reference parameters with pointers, but that's what a reference parameter always does, whether it's a vector or an int or this thing. So it's not that different, really. And so by simply adding this ampersand here, you have to be careful about the order. It's a pointer ampersand, not an ampersand pointer. If you do it in the wrong order, it doesn't work. But simply by making that change, I see you. I'll call you in 1 second. Simply by making that change, what happens to the picture now is the following. So it's the exact same code, but all I did was add an ampersand here. Now, when I say add front list 10, front is not a new pointer that points to the same place as list. Front is an alias for list. They are the same pointer. Do you understand that? That's what a reference parameter is. Now, the same code does something very different. I make the list node temp. I set the temp next to be front, point to the same place as front, so it points there. Now when I say front equals temp, it makes front and list point to there. This arrow should go away here or whatever. But sorry, the diagram should sort of cross out this black arrow here. But now it does update the one from main. That's why this version works. Now, I'm trying to draw you these pictures to see what's going on. These pictures don't work for everyone. I think the short version here, if you're having a little trouble, is to say, look, if you have a method that you are writing, a function that you're writing, that is going to modify a linked list by adding new nodes and pointing to new nodes or deleting nodes, this kind of thing, then you have to make that function take the front pointer as a reference pointer. So if you're changing the list, reference pointer. We didn't need to do that when we called the printing function. We didn't pass that one by reference. The reason is because I wasn't modifying the pointer, I wasn't changing the list. So if you're just looking at the list, reading the list, printing the list, searching the list, you just pass a regular old pointer. If you're going to modify the list, write the list, change the list, pass it by reference to a pointer. So that's kind of the rule that you need to remember to follow consistently in your functions. Now, if you went to section and you wrote problems that read a list, you pass a regular pointer. In section, if you modify the list, you had a reference to a pointer. So your hand was up. Did you have questions still? Yeah. Sorry, you're talking about the printing of list code?
Yeah, like we didn't have any answer on this week. I thought it was still print the original list because this was
Okay. So your question was, why did it print nothing? Why didn't it print the original list? Right. So, okay, the reason it didn't was because I turned off the code that built the list. I thought that if our add front method worked, I could just use it to build the list. So let me change it to do what you might have expected it to do, which would be this code comes back. And so it should print that list now. But then when I try to add front, comma 777, that value, I want that value to appear at the front. So let's see if it does. I mean, it won't. So there, I got the list. It just didn't, I told it to add a value and it didn't do it. But the magic fix here is that add front should take a reference to a pointer. And then, oh, did I break it? Oh, I think it's because I have a prototype and I have a body and they have to match each other. So I think up here where I declare add front, this one also needs to be a reference. If they don't match, you guys have probably had this bug on like homework 1 or 2 or something, right? So, hey, look, it added the thing at the front now. So now it's working. Yeah, question, go ahead. Oh, does it have two names? Well, in this slide, I went out of my way to pick different names because I wanted to make it clear that the name wasn't what matters. You're right that in this code, as add front is executing, for that duration, it has two names. But once add front returns, it goes back to just having one name of list. But I think in some code you can call it front in main, and you can also call it front up here. And it's like you have two fronts that are aliases for each other that are the same. So yeah, it can have two names or two variables that refer to it. Anyway, again, I know this is hard. I know this is confusing. I think just, if you're having a little bit of trouble, the thing to remember for the time being is if I'm going to modify the list, pass the front by reference. Question, yeah?
So in your code, you wrote new node dating 777 for the add front method. Why isn't it adding 777 every time? Why would it really file?
Why isn't it adding 77 every time? Well, I think what I did was I added 4 values the old-fashioned way by just wiring up the nexts, and then here I just a single time added 777 after all of that. So it's just what I did in main, basically. So now that I made that change, I think maybe I could turn this off and I could turn this on, and then maybe the whole list would build properly. Oops. Well, I think what's happening is that if you go into add front, we're setting the value to be that every time, but they pass in the value that they want us to use. Maybe that's what you were asking, maybe. So that's the value to put in the node, not always 777. Ta-da, it works. Okay, cool. Yeah, question?
If we don't want to modify the front with like another element like in the middle of the list, like we don't need to pass the front, do we still need to pass like another element which is not the front by reference?
That's a good question. Yeah, what if I'm writing a method that isn't going to modify the front? What if I'm going to modify the last or the middle or something? Do I still need to pass by reference? That's a great question. I think the answer is sort of no, but sort of yes. And by default, if you're not sure, then yes is a good choice. So let's address that. I'd like to write a method with you guys, a function with you guys called add, which is basically add to the back. So that's not the front anymore, right? So that I think we'll hit the question that you're asking about here. Now I've written it with an ampersand, but maybe we could try to think about if we need that or not. So this is adding something to the end of the list. Got it? Not the front, the end. And adding to an end of a vector is easy. You just put it in the last index, and adding to the end for a vector is the good way, the good case, the fast case. It turns out with a linked list, that's the opposite, that the front is the good case because you're right there and you just add the thing. But with the end, you actually have to hop all the way to the end by saying next, next, next in a loop to get to the end of the list. Do you understand? Like if I want to, don't I have a picture here? Like here, I want to add the value 20. What I got to do is I got to walk all the way to the end and then attach the guy right there, okay? The new guy. So maybe you guys could help me write that code. I mean, I basically have to write a loop to walk to the right place in the list to do the insertion. So I guess the question is, if I have a current variable that's a pointer, where do I want that to be pointing when I'm going to do the insertion? And I guess the corollary to that is what should the loop test be to loop me up to the right place? What do you think? Well, do I want current? I'll write cur because that's easier to spell. Do I want current pointing here? Raise your hand if you think current should point here. No one's raising their hand. Okay. Do I want current to point here? Raise your hand if you think I want current to point there. Some. Sit there completely indifferently if you want me to point current there. Oh, you want that? Oh, never mind. This is like participation for millennials. Or you guys aren't millennials. You're Gen Z, right? Should I make it point here? Raise your hand if you like that one. Now you're scared to raise your hand. You just don't know anymore, do you? Okay, look. We need to add the new guy right here, right? Not drawn to scale. If you want to add a node right there, What that means is you need to be talking to the node right before that. You need to be kind of looking at the last node. Current should be the last node to do this insert, right? So I think that concept makes sense, but which of these loops says to stop when current is the last node? Which of these choices is it? Somebody raise your hand. Somebody brave. What do you think?
I think it's C because you wanted to point to the node before next.
Yeah, you said C. I think you're exactly right. What you want is for current to be looking at a node whose next is null. That's right. So I want current next to be null, which means I want to keep looping as long as that isn't the case. Stop when current next is a null pointer. Now, I guess the reason I'm talking, you might say, well, fine, that makes sense, that's obvious or something. But a lot of students want to pick A. They go, well, keep looping until I see the null. Keep looping until current is the null, right? But if you do that, it doesn't work, because let me try to trace through what that will do. You'll say start current at the front, like start current here, and then you'll say, well, is current null? No. Okay, then go to the next. So go to here. And then you'll say, is current null? No. Okay, go to the next. Well, the next is null, so make current also be null. So making current be null just sort of is like a slash like that. Null doesn't point to any of these nodes. And if you walk all the way until current is null, you sort of fell off the edge of the linked list. And now your pointer doesn't point to any of its nodes. So looping until current is null walks all the way to the end, and it won't be useful for adding something to the end. You need to stop above that element 1 in the diagram there. So adding at the end of a linked list looks something like the following. If we're going to add at the back, what do I call that up here? I call that add. So let's have a list node, current, that starts at the front. And while there is a next node after current, I will say current should go to the next. And now at this point, current points to the last node. As she said, that's where we want to stop. So how do I insert a new node there? If you want both of the pieces on the screen at the same time, I think I can do that. So in this code here, current points there. So now what lines of code do I write to add a new node after that? What do you say?
You would create a new node, and then you would do current next equals that.
Great. Make a new node, put the value that we're adding into that node, and then make current next point to that new node. That's perfect. That's exactly what I want. So make a list node star new node equals a new list node. If you want, you can put the value, the data of the node in the parentheses, like as you're constructing it. So store that value as the data. And now, what should the new node next be? Null, because this guy's going to be at the end of the list. So there's nobody after them. But now what you said was make current next be the new node. Put him after the current, after the last node. Okay. Now, what some people would do is they'd say, well, could I just make current equal the new node? What if I do that? I want to trace this with you to see what that does. If I say current equals new node, wait, sorry, I'm trying to get this all on the screen at the same time here. Okay, here. So right now, current points here. Yeah, that's what we did. And now I make a new node. So I'll call him new, N-E-W, points to a new node, right? And his data stores whatever, and his next is nothing, null. And now if I say current equals new node, that says make this pointer point to where the new node points. So don't point to there anymore, instead point there. What's the effect of this? What does this do? Did it work? Fell off again? Yeah, I mean, that does not add anything to the list. Do you understand? Like the person who's using this list, the person who built this list, the person who's taking care of it, main or whatever, the way that they know what's in the list is they start at the front and they go next and they look through until they hit null, right? That's what's in the list as far as they're concerned. If you start at the front here and you go next, you never see this new node. The new node didn't get like attached to anybody. There's only two ways you can add something to a linked list. You can either make a new node and put it as the front of the list, or you can make a new node and make it be next after an existing node in the list. Those are the only two ways you can modify a linked list. This code doesn't do that. This code takes some other pointer and makes it point to a node, but it doesn't attach the node to the other nodes. That's why it's actually really, really crucial to say current next equals new node. And the difference there is that instead of making current point over here, it says, hey, current, follow your pointer, and then set the next variable of that object to point to this new node. So make this next thing point to the new node. Make this next thing point to the new node like that. Now the new node is part of the list. See the difference? It's a really important difference. I mean, I guess the general rule I would give you is if you ever find yourself saying current equals whatever, that is not going to make a change to the linked list as far as main is concerned. It always has to be current next equals or it has to be front equals. And the reason front equals works is because we're passing front by reference. So that's why it works. This is basically the algorithm for adding something to the end of a linked list, except it's missing an important case. What happens, so, if this algorithm really works, we should be able to use it no matter what. So if I go back to main, if I really want to be able to make a linked list that has 42 and -3 and all that stuff, I should be able to use the add method to accomplish that, right? So I should be able to, oops, what happened? I should be able to say add, like this. I should be able to add 42 and -3 and 17 and 9. I should be able to build the list up from nothing to have stuff in it, right? If I try to do that, I get an error. Welcome to the segmentation fault. This will not be the last time you meet it. The segmentation fault is basically a pointer bug where you have followed a pointer that you shouldn't have followed because the pointer was null or the pointer was garbage or something. It usually means you walked off the end of a linked list and tried to access data found there, or that you tried to follow a null pointer and tried to use it as though it were an object. In Java, they have this concept, it's called a null pointer exception. Most languages have some kind of error that's akin to this. We have line numbers. It says it happened in the add function on line 135. The add function on line 135 is here. Why do you think this code crashed? So it might be helpful to look at main, how main calls this. Main calls this by saying I have a null list and I want to add 42. So I'm basically saying I want 42 to become the only element of the list. It used to be null, now I want it to be a one element list. That doesn't work in this code. What would this code do if front were null? What would be bad in this code? What's wrong with it when front's null? What do you say?
It looks ahead to the sort of next, but there is nothing to look at.
That's right. So he said it sets current to the front, which is null, and then it says, hey, null, what's the next after you? There's no next after null. You can't follow a null pointer and look at a data there or a next that's found there. There's no object there to talk to. Do you understand? So this code doesn't work when the front of the list is null. Okay, that's all right. We can fix it. It's okay. It's just I want you to see this, that this is a bug, and that's why it's crashing. Now, the general principle that you can extract out of this bug that we're discovering is that most linked list code has to think about different cases, different states that the list can be in. So most linked list code, you should think to yourself, what if the list was empty or null? What if there was only one element in the list? What if there were a lot of elements in the list? Another thing you could ask about is what if I'm doing this operation at the front versus what if I'm doing it in the middle versus what if I'm doing it at the end? You were asking about that a few minutes ago. That's a good way to think about this. So think about different sizes and think about different indexes or locations that you might be operating on. This code works great for the general case. I think if I go back to main and I restore my original code that makes a list, and then from there, if I try to add some stuff, I think that code would work. Oops, sorry, I have a duplicate variable. I think that code, see, it did add the stuff that I tried to add. So add works, except it doesn't work with the null list. So here's all you got to do. You got to say, if the front is a null pointer, let's handle that case differently. So this code that we wrote before was sort of for the non-empty list. This is for the general case, the case that we most often would think of. But this is an empty list. If you're adding something to the end of an empty list, how do you do that? With the glasses, yeah, go ahead. Make front point at a new node. That's right. The front is null currently. Change it from being null to being a pointer to this new node that I'm creating. So the case that we're describing looks like this. It was null, but instead make it point to a new node. So I don't have to do any looping. I don't have to do any next. I don't have to have a current variable. Those are things that you need if you need to get farther along in the list. I don't need to do that because there is no farther along to get to. There's no list. It's empty. It's null. Make it unnull by making a new node and by making the front point to that new node. Else, if it isn't null, walk to the end, do the stuff we wrote before. Now I think add should just work in all the different cases. If I jump back up to main, I would hope that maybe I could use this old approach that I had here where I start null and I just add stuff. Does it work? Hey, there it is. So now it's adding nodes. Now it's working. Yeah, question? Why did I have else? Let me go back to that. We can look at it. So why do I say else? Well, I guess if I didn't have else, it would always run this bottom chunk, and then it would add it to the front, and it would walk and add it to the end also. You know what I mean? So I only want to do one of those two things, I think. Did I misunderstand your question? Or? I mean, basically, if the list is empty, do that one line, and if it's not empty, I have to walk to the end and insert it at the end. And so I should pick one of those two branches and not both. Like if I do the one at the front, I don't want to do the one where I walk to the end, because there's no, I already added it, I'm already done. Yeah?
If you instead put the check in the while loop, like while front equals not null pointer, would that have corrected it?
Oh, so could I instead have kind of like patched up this code to sort of work with the case that the front is null? It's possible, sure. But my suggestion would be this is simpler and easier and works better and it's easier to debug. I think trying to make one blob of code like carefully handle a million different cases is prone to error. And I think this is very clean. It's like if there's nothing there, make a node. If there's something there, walk to the end and put it at the end. But this matches much closer to my mental model of what is going on. And I think this sort of template is, if you follow this kind of template, I think you can solve almost any linked list problem in this way. Yeah, question?
Do you have to initialize the front next equal null pointer?
Oh, that's a good question. So since there's nothing after this new node, should I say front next equals null pointer? Technically, no, because the list node class initializes itself to have a null next if you don't set the next. But this would be fine as well to just be really explicit. I don't want there to be any next after that. Yeah, I mean, you could write this out in many steps. You could say something like list node, new node equals a new list node. And then you could say new node data equals this value that you're adding. New node next equals nobody. Front, okay, I want you to be the new node. You could do all of that as separate steps. The list node class that we provided, you can put the data here. You could even put the next here as well. You can initialize some of those things as you create the node. And if you don't supply them, the default data is 0 and the default next is null. So yeah, you don't have to say it, but that's what it's doing implicitly. What else? Yeah.
Here you're never, I guess my approach is you're never like resetting front. Usually we like reset front. And now we just have current and pending current. The current used to be pointing to the last thing, and now it's pointing to this new thing, but like how does that relate to?
Well, how does, okay, so you said we're not resetting front. I mean, remember that the point of this code is to add to the end of the list, right? So I only want to set front if the front is the end, like if there's no list, you know? So if I already have a list with a bunch of nodes, I don't actually want to set the front. I don't want to modify the front because the front is still the same node. 42 should still be in front, so I don't want to set front equals anything. I want to say front, next, 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 next. E should be the new. So if I set current as front and I walk current to the end and then I set current next to be the new thing, that will also affect what you see when you follow next chain of pointers after front as well. So that's how the list is getting like changed basically. So I start at the front, I walk to the next a lot, and then I set the next of that node. Since I started at front and we're all pointing to the same objects, I will modify the linked list of front as well. That's the sharing here. Okay. Look, it's hard. This is hard stuff. You have to practice this. You have to draw a lot of pictures. We're practicing it. That's what we're doing. Well, I want to talk about removal for a few minutes. I got a few minutes of class left here. Let's talk about, I don't want to do that one. I want to do, no, I don't want to do that one either. I want to do remove. So actually, this one is like a general remove that takes an index. But actually, I think what I want to do instead is I want to write remove front, remove back. If we have time, we could write more. But let's think about how would I remove the front node. If you just call remove front and you pass front, how do you do it? What do you think? I mean, I can show you the heading of it if you want. Like here, I'll say what? Remove front. I don't have a heading for it, but I'll just take the add front. Oh, I have remove front. Here it is, and it should be a reference. So remove front. Remove the first value from the list. How do I do it?
Just want to adjust the front pointer so that it skips the first element and then looks to the second one.
That sounds great. So since I'm changing the front of the list, I want the front to be a different thing. I should say front equals. Now, you might say, is it front equals or is it front next equals? I mean, what you said was change front to equal something new. And I think that's right. If you say front next equals, that would modify what this first blue box points at. So that would change the second node of the list. But setting front equals could change what the first value of the list is. So what do I want to set front equal to? Front.next. Front should point to the place that front next points. That's what I want to do here. So front equals front next. Well, that one wasn't very hard. All right, I guess we solved that one early. Maybe we just go get some lunch or what? We're not quite, that's pretty close. There's a couple things about this that need to be affected still. Yeah, what were you going to say?
So like in 106A, they talked about like garbage collection, where if we had an object we didn't use, it would delete it. In C++, is this node just like taking up space, or is it like automatically destroyed as well?
Yeah, so you asked about memory and garbage and this kind of thing, and you're right that this is bad. It has a bug that's called a memory leak. I don't know if I have a slide on it. I think I do. I mean, I want to talk about it with you. Where is it? Let me see real quick. Yeah, okay, I don't know if I have a slide, but look. If you delete a node, if you delete the node at the front here, you say, I want front to point to front next, like this, then you have effectively, you don't have a pointer to this guy anymore, right? But he's still sitting in the memory of the computer. C++, unfortunately, will then abandon that memory for the lifetime of your program, and it will no longer be usable for anything. It will just be dead garbage memory that can't be reused. It won't ruin your computer or something. It won't break your computer. It just, until your program exits, that memory will be unusable for anything else. So that's bad. That's called a memory leak. Java and other languages have automatic mechanisms to come along and they detect that the memory is dead, not being used, and they clean it up for you and they reclaim it. C++ doesn't have that concept. The way that we reclaim this memory in C++ is that there's a command called delete. If you say delete, it will tell C++ that you're not using that memory anymore. So if you pass a pointer to the delete keyword, it will throw it out. So if I say front equals a new node, second equals a new node, and front next equals second, If I say delete second, that tells C++, I'm not using this node anymore. Take it back. You can have it back. Now, the weird thing about that is I still have a pointer to it, but the memory is no longer mine, so I shouldn't follow that pointer, but I still have a pointer to it. The equivalent of this command in our function that we're writing would be that we would want to delete the front, but you have to be careful because you can't say delete front and then front equals front next, because this would be like I'm using front after I deleted him. You know what I mean? Like if I wanna go to this second node here, if I say, hey, delete the front, then it totally gets rid of this node and all of the information it used to contain. Now if I try to say go to the next of it, the next was in the thing I threw out. Do you understand? So I can't delete it and then go to the next. But I also can't invert the order either. Because if I do front equals front next and then delete, it'll move this like that, and then it'll say delete your next, which will delete this guy. So neither of those two are the right thing. So clearly I cannot choose the goblet in front of me. Never mind, it's a Princess Bride reference. No. Do people still know that movie? Go watch The Princess Bride. If you haven't seen it, like just leave now. Don't even listen to the rest of the lecture and go watch it right now. It's great. One of Andre the Giant's better acting performances. Anyway, okay, so neither of those two orders of lines will work, but we do need to clean up this memory. So the pattern that I like to use is I like to keep a temporary pointer to the old node, then move to the next, then delete the old node by using that copy pointer. So I usually, just for real clarity, I like to say list node trash equals front. So that's my kind of temporary pointer to the guy that I'm deleting. Now move the front to the next, and now take out the trash. Delete the trash. So if you look at section solutions or other lecture examples, you'll often see that pattern, delete trash. So that's remove front. That's the main thing that's wrong with remove front, is that it didn't clean up its memory after itself. There's another problem with remove front. There's a case of a list that it doesn't do the right thing. No? Yeah, if the list is already empty, is that what you were going to say too? Yeah, if the list is already empty, I shouldn't be doing this. Do you understand? What will happen if I try to do this when the list is empty? Segmentation fault, right? It'll crash, it'll do bad stuff. So let's handle that. I mean, it's not very much to do. Just say if front isn't null, then do this. It's always useful to think about different cases. So you might ask, okay, I thought about the zero node case. I thought about the lots of nodes case, the general case. What if it's only one node in the list? Will this still work? What if it's only one node? That's always a case to think about. So I guess my point is that front, I'll just write F, points to one box, which has some kind of data inside, and it has a null next. So front is not a null pointer, so it will enter this. So now I'll say trash equals front, so I'll call that T. Trash points here. Front equals front next. If there's no next node, what does that line of code mean? What does that do? What does it set front to be? Null. Is that what I want? Right, I do want that, right? Make front be null. Make front point where that points, which is nothing, null. And now delete trash, so get rid of this guy. And so basically throw this away like this, right? And when I'm done, I have null front. That's what I want, right? So the one node case already works. The if statement fixes the zero node case, and the body of the if handles the multiple nodes, the main case, the general case. Okay? Now, if we were going to do remove back, which we don't have time for, we would use that same approach with current, where we would walk current to the end, make a trash pointer, point the current next around it, and delete the trash. It would be the same approach. Okay, well, I'm out of time. I'll post all this code on the website. You can look at it over the weekend if you like. I will see you on Monday. Have a good weekend.